Okay, so use the systematic treatment of equilibrium to determine the pH and concentrations of species in a 1 liter solution containing 0.035 moles of HOBr, which is your acid, and 0.0070 moles of NaOH, which is your strong base. Consider only the acid-base chemistry, so we don't have to consider any other chemistry that could happen in this system that would produce things that would tilt these equilibriums considerably. We can just ignore that. And we can ignore ion pairing and activity coefficients. That's nice. That really reduces the amount of work we need to do. The pKa for HOBr is 8.63. Okay, so this problem, actually, there's two ways you can go about this. There's the Excel solver, like the entire chapter is really about, which this would be good practice to do, and I'll show you a bit. But I want to point out something, and that's that you have a strong base here, which is 0.0070 moles of NaOH. What that means is there's no other form of sodium in this problem. And so the Na plus will automatically, it should work out to something that's essentially this number right here. And so we go 1, 2, 3. If you want to put in scientific notation, it would be 7.0 actually would be the correct number, times 10 to the negative third, because that is soluble with all the other species in here. Also, because the pKa would be 8.63, that would make it a Ka of 10 to the negative 8.63, which is a very small Ka. That means this acid is a very weak acid. So this number right here is much, much larger. This base is going to react with your acid here. And so just using logic, you could figure out that pretty much what happens here is 1-to-1 ratio of reaction. The vast majority of your deprotonated conjugate base here, the OBr, which is down here, is just going to be a straight up 1-to-1 ratio of the reaction. So you can pretty much just take this number down here, put it down here, and that's going to be the vast majority, 99%. You won't have anything that you would just round this right back down if you were to try to figure out the Ka of this and figure out how much actually breaks apart on its own. So you can actually get away with filling out most of this problem just with understanding weak acid, very weak acid, strong base, and how those relate together. So again, the sodium really can just come straight from there. That's the only form of sodium. But we'll prove it in a little bit. And the deprotonated conjugate base of this acid here, the vast majority is going to be made from the reaction with the NaOH, meaning that that number right here pretty much just goes right back down here because it's a 1-to-1 ratio. And this is 1 liter, by the way. So it's the moles here divided by 1, which gives you the same number for molarities. That means that the HOBr that stays together is just the difference. So your 0.035 minus the 0.007 would give you the stuff that remains staying together. So that actually gives you most of the information that you need here. And you could actually just work these out fairly simple in a simple ice problem, because once you get one, you get the other. But since we don't want to go ahead and just use the simple, straightforward method to do this, we want to practice what's actually going on in this chapter. This problem just happens to be one that could be worked out in a much, much simpler logical fashion. But let's go ahead and look at what we would need to do to solve this problem if it was more complex. So the first thing you should always do for these systems is state explicitly what's going on. So, for example, we have two equilibriums that are interacting. We have the acid dissociation equilibrium, which would be your acid losing a proton. And that has a pK of 8.63 that you were given. We also, in every water aqueous solution, those are in water, so in water, these equilibria are acting on the water equilibrium. And so for every water-based solution, we have the water autoionization reaction, which is water donating its proton, which would give you remaining OH minus as the conjugate base. And again, that's always going to give you the pKw, which is the 14. That's where you get that 14 equals pH plus POH. Or you get the Kw would equal 10 to the negative 14 equals the H plus concentration times the OH minus concentration. That's where all that always comes from, because all these always take place through water equilibrium. That's what you're actually affecting when you're doing these. So we write those out explicitly. So we have all these terms, we have all of this work that we can look at. We would then go ahead and write out explicitly the other truths, the other things that would be a fact of this. So for example, the charge balanced equation always has to be a fact of every solution, i.e. the negative charges have to equal the positive charges in a neutral solution, in an overall neutral solution, which practically all solutions are overall neutral.